All right, so for this question, we are going to find the force of tension in the wire, and then we're also going to find the force of that hinge. So in this particular scenario, we have a wall, a wire attached, holding up a uniform beam, and then here we have our hinge. So what we want to note for this problem is this is a torque problem. So if the wire were to give out, we would move it like this way. If the wire were to become stronger than that force of gravity, we would be moving this way. So there's torque involved. So we need to figure out that the sum of our torques, the net sum of our torques, is equal to that I times A being angular acceleration. Well, because this problem is in static equilibrium, it means it's not moving. So therefore, our acceleration or angular acceleration is 0. Therefore, we can know that the sum of our torques is going to be equal to 0. And this will kind of help us set up an equation to solve for this force of tension. When asked to find the force of tension and the force of hinge, we always want to find that force of tension first. And the first step usually is to establish an axis of rotation or a pivot point. This means a point of axis where this beam will rotate about if either the wire were to win and become stronger, or if the wire were to give out. Which way would we rotate? I will always establish my axis of rotation at the hinge. When finding our torques, we need to keep in mind our force multiplied by our lever arm or radius or length from that hinge. So this is really important to note because in this case, our hinge is at our point of axis of rotation. Therefore, we neglect that. And the reason being, it's because its distance is 0 from itself. Therefore, we would be multiplying by 0. So when finding force of tension, we don't need to take into consideration the force of hinge because it will be canceled out by its radius or its length, which is 0. Therefore, we only have two forces left when we were looking at our sum of our torques or sum of our forces. So obviously we have our force tension. Luckily, we are given this angle of 55 degrees, and we typically always use sine. Remember, sine is giving us our opposite, and then our hypotenuse, which we're solving for. And then we also need to take into consider our length from our axis of rotation. So let's go ahead and set that force up, our force of tension. So this is actually what we're solving for, our force of tension, but there's some stuff we know. So force of tension, right? This is our variable. This is what we're looking for. But we know it has to be sine of 55 because it's oriented at an angle. And then we also need to multiply by that length, which is 4 meters, because the entire beam is 4 meters. Our axis of rotation is at the far left end. Therefore, because this wire attaches at the far right end, our axis, it is 4 meters from our axis of rotation, or our pivot point. Now we need to establish whether or not this is negative or positive. You can use a right-hand rule, or you can simply just determine whether or not it is going to be rotating clockwise or counterclockwise. The way I like to think about this is if the wire were to win. So let's say the wire becomes stronger and takes us out of static equilibrium. We're going to be moving counterclockwise. The beam will move this way if the wire wins. Counterclockwise correlates to positive numbers. So this whole thing is positive. Now we're left with just one more force to take into consideration on this same side of the equation, set equal to 0 because our sum of torques are equal to 0 because we're in static equilibrium. Therefore, acceleration or angular acceleration is 0. So our next force is just our force due to gravity. Force due to gravity always acts on the center of mass because we know this is a uniform beam. The weight is not unevenly distributed. So we need to take into consideration the weight of the beam as well as the distance of the beam. That force due to gravity. So the weight of the beam is going to be 5 kilograms, which is given. Acceleration due to gravity is 9.8 meters per second squared. And then multiplied by our distance, it's only 4 meters because it is the halfway point of our beam, which is 2 meters away from our axis of rotation, which is the hinge. So this is going to be 2 meters. Now we need to understand if this is negative or positive. Well, if force gravity were to win and overtake the wire, we're going to move this way. And this way is clockwise. Therefore, it's a negative. So this is all set equal to 0 because this is our sum of our torques. So now what we do is we just solve. So I'm going to multiply our 5 times our 9.8 times our 2 and just add that to the other side of the equation. Therefore, we have 98, which is the multiplication of these three together, equal to our force tension, which we're solving for, sine of 55 degrees multiplied by our 4 meters. So now we're just going to divide that 98 by that sine 55 degrees 4 meters. So we're going to get sine 55 degrees, multiply that by 4. Then we're going to take our 98, divide by this, and that gives us our force of tension equal to 29.91 rounded, and that's newtons. So our force of our tension in our wire is 29.91 newtons. The reason we don't need to take any components of our force due to gravity is because our beam is already entirely in the x direction, meaning it's oriented like so. If the beam were to be, sometimes you'll see problems where the beam is rotated this way, then we need to take into consideration because our equation defines that it's the perpendiculars of one another. So the reason we didn't use sine or cosine for our force due to gravity here is because it's already entirely x, and we already found this sine opposite component of our force tension, therefore they are perpendicular of one another. So that is going to be your final answer for when it asks to find the force of the tension in the wire. Oftentimes there will be a part B or a second portion to the same question, same scenario, that will ask to find the force at the hinge. So we know that the force of the hinge is helping keep this beam up. It has a y component and it has an x component. Obviously, it has a magnitude of both as well going this way. So we need to take into consideration that y and that x component before we can find the magnitude of the both. So force of hinge in the x direction, okay, so this is preventing it from moving in the x direction, has to be equal to our force of tension in the x direction. The reason this is because we're in static equilibrium. So the way that the wire is pulling this way in the x direction, the hinge needs to be pushing the opposite way in the x direction, or else we'd be moving one side or another. So all we have to do is find that force tension in the x direction, and then we can find our force of hinge in that same x direction, because those two are equal as we just explained. So because we have our force tension as 29.9, we can just use components to find that. We have this here is our little triangle. Obviously we know this is 90, this is given as 55. So we could find that angle just by doing 90 plus 50 minus 180, which is 40. It's not necessarily needed, but it's nice to have every component of the triangle. So now that we have that established, we can solve for that x component. So we need to find this guy. So we can use cosine 55 because that's adjacent, or we can use sine of 40. So let's just use cosine of 55. So it's just going to be our 29.91 cosine 55 again. The reason we can do that is because we're finding adjacent. We could also use sine if we use the 40 because that's opposite. So I'm just going to do 29.91 cosine of 55. We get force tension in the x direction as 17.156, which is also equal to our force hinge in x direction. So 17.157, we'll round there, newtons. All right, cool. We found our x component. Now we just need to find our y component. So when we think about what's acting in our y direction, well, there's three things acting in the y direction. We have our force hinge, y direction, acting up, trying to prevent that force gravity from dropping the beam. We also have our force tension, y direction, acting up. And then the only thing acting down is our force due to gravity. So mass times gravity, right? So these two things are trying to hold it up. these two things are, this one thing is trying to pull it down. So let's just find our force tension in the y direction and then multiply mass by gravity and then subtract this from this, and then we'll get our force of hinge in the y direction. So force tension y direction, same thing. Let's use that 55 degrees, but let's use sine. So 29.91 sine of our 55 degrees. Again, because sine opposite from that 55 degrees, y component. 29.91 sine 55. We get 24.5 plus our force hinge y. What we're looking for is equal to, let's do mass times gravity, 5 times 9.8, perfect, 49. So it's 49 subtracted from 24.5, and there we have it. Our force hinge in the y direction is equal to 24.499 newtons. So this is pretty much it. We have found our force hinge in the x direction. We found our force hinge in the y direction. Now, sometimes the problem will ask to find the magnitude of the both, or it'll ask for components. You just need to know which it is asking for. If this 55 degrees here, our triangle, we can note that this is 55 degrees as well. So now what we can do is we're solving for this component. We have our y as 24 we'll round to 5, and then we have our x as 17 we'll round to 2. So it's just simple Pythagorean, a squared plus b squared is equal to c squared. So we'll do our 17.2 squared and then our 24.5 squared, add those, and now that's equal to c squared, so just square root that for our answer. So our answer is 29.93 newtons for our force of our hinge.